Hello there, welcome to the June 2018 applied paper. Here we're looking at question 8. A particle P moves with constant acceleration. At time t equals 0, the particle is at O and is moving with velocity of 2I minus 3j meters per second. At time t equals 2, P is at the point A with position vector 7I minus 10j meters. Show that the magnitude of acceleration of P is 2.5 meters per second squared. Well, in the question here, that was the clue of this question here was right at the start, constant acceleration. So what that means is we can use any of our Suvat formulas in this question here. Let's have a think about what variables we do have. Do we have S, U, V, A, or T? So we have T is equal to 2. It starts at position O and is moving with velocity 2I minus 3j. So the initial speed is initial velocity is 2I minus 3j. At point A, it is at position vector 7I minus 10j, so that's the distance that it's moved, and we want to find the acceleration, so we want to use the formula linking S, U, A, and T together, so that's going to be S equals UT plus half AT squared. Okay, let's go for it then. So it's going to be, in fact, what I think I'll do here is I'll use vertical column vectors for this question here. So it's going to equal 7 minus 10, that's representing 7I minus 10j. U is going to be times by t, so it's going to be 2 lots of 2 minus 3, and then it's going to be a half times 2 squared, which is actually 4, so half of 4 is 2. I could just put that in there originally as 2a. Now a here is actually going to be a vector as well, and then we'll just work out the magnitude of it at the end. So I'm now going to move all of this stuff here onto the left hand side, so it's going to be 7 minus 2 times 2, which is 4, so that's going to be 3, and minus 10 minus 6, that's going to be add 6, so that's now going to be minus 4 when you add 6 to it, and that's going to equal 2a, so therefore the vector of acceleration a is going to be 1.5 minus 2, so therefore the magnitude of acceleration a is going to be the square root of 1.5 squared add minus 2 squared. And let's type that into the calculator. Square root 1.5 squared add 2 squared equals 2.5 exactly. So there we are. So 2.5 is the answer to this question here. And feel free to use this kind of column notation for vectors here to represent your i's and j's if you wish to. I find it a bit easier to represent my work. Gets rid of the i's and j's from the question. Okay, let's move on to part B now. At the instant when P leaves point A, so I just want to make a note of what point A was again. Point A was 7 minus 10, so 7 minus 10, just in case that's helpful. The acceleration of P changes so that P now moves with constant velocity of 4I plus 8.8j meters per second squared. At the instant when P reaches the point B, the direction of motion of P is northeast. So what we want to know, which way is northeast to start with? It's going to be north and east, so the direction of motion will be in that direction there. So it doesn't tell us what the magnitude is, but it's just going to be in a kind of like the vector AA, where the same amount east will be travelled north as well, or will be travelling north because it's a velocity vector. So the direction of motion is northeast. Find the time it takes for P to travel from A to B. So I think what we need here is to use so this is constant acceleration, so we can still use our Suvat formulas. Now, in this question here, we're going to start from the final velocity that we were at before. So actually, it might be helpful to come back at this part here and work out what v was equal to. So if we use v equals u plus at, then that's going to give us v equals 2 minus 3 lots of 2 times the vector a, and that was 1.5 minus 2. So if we add this together, we get the velocity vector, which is equal to 2 plus 3, which is 5, and minus 3 minus 4, that would be minus 7. Okay, so what that means is the speed, or the velocity vector at point A is 5 minus 7. So what that means is that the new initial velocity will be 5 minus 7 here. We know the acceleration is going to be 8.8. We don't know what the time is, but what we want the final velocity to be is, I'm not representing A for acceleration here, it's just A for a constant A, but some direction that's travelling northeast where the east component is the same as the north component, and that will be directly northeast. So again, I think we need to use v equals u plus at on this one. V equals u plus at. The vectors are v, u, a, and t. The vector v is going to be a. The vector u is going to be 5 minus 7. The vector a is going to be 4, 8.8, and then whatever that will be times by t. So let's now expand this right-hand side here. So that's going to be 5 plus 4t, and the second one, the one on the j vector, is going to be minus 7 plus 8.8t. Now, if it's travelling in the northeast direction, then we'll need to find the time at which the east component is equal to the north component. So therefore what we can now say is that 5 plus 4t is going to be equal to minus 7 plus 8.8t. Now let's just explain where this equation has come from. What I've done here is I've set the east component equal to the north component, and if it's travelling northeast exactly, then the north component will be equal to the east component. So therefore the equations will be equal to each other. So if I now subtract this 4t onto the right hand side, that's going to be 4.8t. Add the 7 onto the other side and you get 12. Divide 12 by 4.8, so 12 divided by 4.8 is 2.5 again. So it's going to be t equals 5 over 2. Now bear in mind that we already, no, in fact no, that's just 2.5. Now I was thinking we may have to subtract 2 because of the 2 seconds from before, but no, I think it's just 2.5 seconds as our answer for this question here. Lovely, so there we are, that's our answer for question 8 there, worth 8 marks in total. Let's now move on to question 9.